Okie dokie. All right, let's look at one more thing first. Okie dokie, good morning. Hi, little Oz. Today we are going to kind of finish up chapter 5B. Can't remember all the letters and numbers myself, so. But there's two things that we're going to essentially talk about today. The first one is going to be electronegativity. We'll define that in a moment. And then we're going to talk about polarity of molecules. And we're going to see that the polarity of molecules will help us learn a little bit about their properties. Okay, so let's see. Time to close the door. Okay, so electronegativity. Let's take a look at that. We're going to see that this word means the tendency of an element to draw electrons toward itself in a covalent bond. So that is more of a formal happy science definition, but we can think about it this way also. These ones could be what you might think of as selfish elements, meaning they want the electrons for themselves, they don't want to share. And so we have already kind of talked about some trends in the periodic table. And guess what? It turns out that fluorine is the most electronegative element. So we saw fluorine was also the smallest of our elements that we're looking at on the periodic table, of course, excepting the noble gases. And we're kind of ignoring hydrogen as well. We also saw that it was the least metallic element. And we also saw that it had the highest ionization energy. So we now have one more thing to say about fluorine. It is the most electronegative element, which means that it will try and kind of hog the electrons. So in a covalent bond, where they're sharing a pair of electrons, we're going to see that very often different elements may kind of pull them towards each other a little bit more unfairly. Good morning, Maya. So periodic table real quick. Haven't had to draw one of these for a while. Here's fluorine again. Here's francium. As always, we're going to see that the electronegativity increases as we go up the periodic table and to the right. And in fact, on your homework, in the thousands of pages therein, where did I opened it. Where did it go? Here it is. You're going to see that on page 78, half of the page is taken up by a table with values for electronegativity. And so, what am I doing? I can open it on this computer. How silly of me. I can just show you right here. Maybe. Actually, I don't have it saved on this computer. Anyways, you can look at your homework yourself. So you're going to see that we have essentially values ranging from, fluorine is usually described at about 4. These are not numbers you will need to memorize whatsoever at all. And francium is not even on this thing, but it would be like, it's going to be less than 0.82. They've stopped at rubidium on this particular short little table. However, if you just Google like electronegativity based on the elements or whatever, or if you look on your handy dandy apps, which I guess I can do, most of them will show you electronegativity values. So let's see, how would we do it on this particular table? This is on atomic weight, electronegativity. Here we go. So if we find fluorine here, usually that's about 4. We're going to see that one has the highest electronegativity. This is like a really weird way of displaying this. I wonder if I could display it on the periodic table. Or it just kills itself. Thanks. Okay, well, regardless, different periodic tables will show different things. So you can look up those values if you really want to see what they look like number-wise. But suffice it to say that fluorine will be your most electronegative element, followed by oxygen. Oxygen is about 3.5 or so. These guys are going to kind of be your most electronegative elements. So oxygen is about 3.5, and then these guys are both about 3. And so we're going to see that in bonds, these particular 4 elements will tend to be... yeah, sure. So those particular elements, fluorine, oxygen, nitrogen, and chlorine will tend to be the most electronegative that we're going to see. And so they are going to be the selfish ones. So they're the ones in a covalent bond that are going to want to try to steal electrons towards themselves. And so we're going to see kind of the effects that this is going to have. And so, yeah, so these are going to be our kind of how we're going to judge how selfish these elements are. Okay. One thing to note, that hydrogen and carbon are very similar or in electronegativity. We're going to see that's going to be important later. Okay, so what this means for us is if we take a handy dandy molecule here, water, we're going to see that oxygen has an electronegativity of about 3.5, and hydrogen's is about 2.1 or so. Just guesstimating these, I mean, you don't need to memorize these numbers whatsoever. But I do want you to understand the trend. Of course, you can see oxygen is definitely more to the right on the periodic table, so it should be more electronegative, which it is. We're going to see that that means oxygen will draw shared electrons closer to itself. So we can imagine that in both of these covalent bonds, the oxygen is kind of drawing in the electrons from hydrogen. So they're not being shared equally. It's not a 50-50, split. These are actually going to hang out with oxygen a little bit more. And as a result, we're going to see that oxygen, by having more electrons, will have what's called a partial negative charge. So that symbol, that's a Greek letter delta, lowercase. And so we're going to see that because the oxygen kind of hogs the electrons, it's just going to be a little bit negatively charged. Not at all a full negative charge like it is with a metal, but it'll just be very slightly negative. And as a result, because these hydrogens are going to lose the electrons a little bit, those will be a little bit positive. And so these are going to result in partial charges. And that's delta. If you imagine writing an S and then just finishing the loop, that's how I write delta. So like an S and then just like finish the loop. So it looks like, yeah, delta. So lowercase delta. Capital delta is a triangle. And so we're going to see that this can result in what are called polar bonds. And so if we have a covalent bond with atoms of different electronegativities, we're going to see we kind of have a rough idea of kind of how we can define different types of bonds. So if we see that the electronegativity difference of the two elements we're looking at is between 0 to about 0.4, we usually will define that as a nonpolar bond. Nonpolar means these elements are close enough in electronegativity that they're not really going to have an unfair sharing of electrons. They're going to be pretty close to sharing them equally. And as a result, we're not really going to have these charges, these partial charges on those. And usually the other criteria is if it goes to about 1.9 in the electronegativity difference, that's going to be a polar covalent bond. Of course, this is covalent as well. Sorry, I forgot that word. And then if it's just bigger than 1.9, it's going to be completely ionic. So we're going to see this is kind of like a spectrum. It's, you know, at one end we have completely non-polar things, and on the other end we have completely ionic things. So ionic things have completely taken the electrons away. So what this means is nonpolar, which means equal sharing, and we have no partial charges. A polar bond means unequal sharing, and therefore we will have partial charges. And of course, an ionic bond, we have complete electron transfer. And those we have full charges. So that would be like sodium completely giving away an electron to chlorine. Now we have a completely positive, an entire positive charge on sodium, an entire negative charge on chlorine. That's an ionic bond. Okay, so that's what these are going to mean. So if we look at the electronegativity difference between water, or hydrogen and oxygen, here's our water molecule again. We saw that oxygen was about 3.5, hydrogen about 2.1. The difference in those is 1.4, which would put us at polar covalent, according to this kind of rough sketch of the ranges for these kind of categories. Again, this is in reality, it's kind of a spectrum. So we're going to see that, you know, if it's if it's right at 0.4, for example, you could make good arguments for either side. But when it's pretty smack dab in the middle of a range like this one is, it's for sure polar covalent. And just so you know, the more electronegative atom gets the partial negative charge, the other atom gets partial positive. Okay, and so that's why we saw earlier that we had those kind of partial charges on our water molecule. Alrighty, let's do some practice. So here's a molecule, CCl4, carbon tetrachloride. Let's see, does this have polar bonds? And I will just tell you right now, the electronegativity of chlorine is about 3. For carbon, it's about 2.4, thereabouts. Again, these would be on a handy-dandy table for you. It looks like they've been a little bit updated since I've last taken chemistry, but that's okay. I'm giving you rough ideas, but if you look on the table that's on your homework, you'll see that you have more exact numbers. And so we're going to look at the difference. So 3 minus 2.4 is 0.6, which tells us these are going to be polar bonds. And so we go back up. We can see here there are our ranges. So if it's less than 0.4, it's going to be nonpolar. We're going to see a lot of things will fall under this polar category. And then ionic ones would be completely, metal, non-metal. So we're not really going to see a lot of ionic ones in this chapter, again, just because we've already talked about ionic compounds. So we're mostly just looking if it's polar or non-polar. So that tells us that a CCl bond is a polar bond. So a bond from carbon to chlorine will be polar. How about methane? Ooh, shame on me, I'm using different colors now. Hydrogen is about 2.1, carbon is about 2.4. These don't have units, by the way. This is kind of just a relative scale, so there's no units that we have to worry about. We look at the difference. By the way, we typically just do the bigger one first, just because we like things to be positive. If you do get a negative one, just make it an absolute value, because we're looking at the magnitude of the electronegativity difference. So we're not really interested in if it's positive or negative. There's not really a point to doing it otherwise. So just look at how big the number is. So it's 0.3. And if we go up to our little scale here, it says if it's less than 0.4, it's going to be nonpolar. And so we're going to see that a CH bond is nonpolar. Because the electronegativities of the two atoms are pretty close together. And as a result, we're not going to have necessarily uneven sharing in between them. So does that kind of make sense? That's why we're doing this easy math here, and just and taking a look at what our number gives us. So far, so good? So then we see that bonds can be polar or nonpolar. Molecules can also be polar or nonpolar. Let's take a look at another example of a molecule. One we did yesterday, or possibly the day before, carbon dioxide. So let's look if a carbon-oxygen bond, if that's polar or not. So if we take a look at the electronegativities, again, I'm going to give these to you, or you'll have a table. Don't bother memorizing anything like this. Carbon is 2.4. What do we think? Is this going to be a polar bond or a non-polar bond? Or ionic, I guess. What do we think? Yeah, for sure. It's smack dab again in the middle of that polar range. So we're going to see that this will be a polar bond. And so I'm just going to go ahead and erase these numbers just so I have a little bit more room. Remember that the more electronegative element is going to have the partial negative charge, and the other one, the less electronegative, will have the partial positive. What we can see here, however, is we have an oxygen pulling carbon's electrons from the left, and we have an oxygen pulling carbon's electrons from the right. And so if we think about what this means, is normally I would have some of you pull me in class. One of you would pull me to the left, the other would pull me to the right. We're going to see if you're both pulling on me from opposite directions. Overall, nothing's moving. So if you want to think about it, the electrons on carbon are being pulled to the left by an oxygen. They're also being pulled to the right. And since the oxygens are the same as each other, it's being pulled in two different directions at once for the same strength, basically. And what that means is that overall, no electrons are being pulled. I know that sounds very strange, but we're going to see that if we kind of draw where the electrons are going, that we can see that carbon's electrons are being pulled either direction. Overall, these guys will cancel each other out. And so that means there is no tugging of the electrons. You can think of it as like a tug of war where your teams on either side are clones of each other. And so if they're all at the same strength and everything, and everyone's pulling the rope, the rope is not going to move anywhere because they're equally matched. And so this means that this molecule is non-polar overall. So while carbon dioxide has a polar bond between carbon and oxygen, and another polar bond on the other side, overall the molecule is non-polar because it's being pulled in the same, manner from both sides. And so we're going to see for a molecule to be polar, what's the best way to explain this to you? We'll make it easy. How about this? It must not be symmetrical. So symmetrical molecules will be nonpolar. We're going to go ahead and take a look at some of these. So we're going to use the symmetry of the molecule to tell us if it's polar or not. So let's look at that carbon dioxide again. If we go back to symmetry class, I don't know, when do we learn symmetry? Geometry maybe? I don't know. Let's see. If we kind of cut this molecule apart, we see kind of no matter which way we cut it, it's going to be the same on the other side. So we kind of have mirror images happening here. So this molecule is symmetrical. No matter which way we cut it, we're going to get kind of the same thing on both sides. So if we cut it right down the middle, we have an oxygen on each side, right? They're the same, so it is symmetrical. And since it is symmetrical, that means it's nonpolar. I'm going to just erase those lines. Oh my gosh, really? Let's do it one by one. I don't want them to like interfere with your notes. But that's the idea. And so we can go ahead and expand this further. We saw we had carbon tetrachloride we did earlier. We found that, again, we had a polar bond between carbon and chlorine, for sure. But if we look at this molecule, again, it's symmetrical, right? Let's draw a line through it. Do we have the same thing on both sides of that line? We do. And so this means that because it's symmetrical, and therefore it is going to be nonpolar. The diagram above it. Which diagram? Above main. Like the carbon dioxide molecule, is that what you mean? So yeah, carbon dioxide. Okay. Yes, so essentially all we're doing here is we are looking at whether our molecules are symmetrical or not. And that's going to give us some insight into whether it is polar or not. And we're going to see that the polarity will be an important factor in predicting some properties later. Okay, cool. Great. So, because this molecule is symmetrical, it is going to be nonpolar. Let's see what happens if we swap one of these out with a hydrogen. So that one, it was erased. But remember what you can always do, even though it's live right now, you can always pause it and kind of go back in time. It's pretty cool with Twitch. So let's look if this molecule is polar or not. Let's take a look. Draw a line through it. Of course, our line has to go through the center of the molecule. You can't just draw a random line. So is this molecule going to be symmetrical? Is it the same on both sides? Doesn't look like it to me. We have a hydrogen on one side, a hydrogen and a chlorine on one side, we have two chlorines on the other side. So, looking at that, which is not symmetrical, and therefore it will be polar. Yes, so that's how we have some evidence that water is polar. So polar things are going to have partial charges, and as a result, they are going to be attracted towards charged things, right? We know that positive and negative attract each other, right? So we're going to see that that balloon thing where I rubbed it on my head created some static electricity, right, in the balloon, and so because electricity involves charged things, that's why the water would be attracted to it. And so if we were to pour carbon tetrachloride, please don't, it's horribly, horribly toxic. But if you were to pour it and put the little source of electricity nearby, it's not going to be attracted towards it at all. So you're going to see, Lamonda, that's going to be one of the properties we have about polar things. But first, let's just do some more examples. Awesome. All right, how about we do ammonia? Do we have exactly the same thing on both sides? Doesn't really look like it to me. We have a lone pair on one side, and we have hydrogens on the other side, right? So this one is not symmetrical. And therefore it is going to be polar as well. Hopefully not too bad. Fun fact for you. Any molecule that has a lone pair on the central atom will be polar. Easy way for us to remember that. So that also tells us that anything that's bent or trigonal pyramid will be polar as well. Because remember, those geometries require that we have a lone pair. Remember that bent could be these two kind of could be bent, right? And trigonal pyramidal was this one. Notice that all of these have lone pairs on them, right? They all have at least one lone pair. And so anything that has those geometries is going to be polar as well. So just another thing, another kind of handy toolkit you have in your pockets to use. Just do one more. Have we done the Lewis structure for SCl2 before? I don't remember. Well, I mean, it doesn't hurt to do it again, I guess. We definitely did selenium dioxide. Okay, we did not do sulfur dichloride. So let's just practice our let's practice our Lewis structure skills just to make sure we haven't forgotten. Remember, we have to count our total electrons. So we have 6 plus 7 plus 7, which equals 20. We draw a skeleton with a single bond in between our elements. So we've used 4 electrons. We're going to want to go ahead and start giving them to the outside. So I gave out 12 more. We have 4 left. So we'll give those to sulfur now. And we can now double check our molecule. Does everything look like it has 8? Looks like it to me. I actually like this drawing. You can see kind of 8 very clearly on all of the atoms. And so this is the molecule we'll end up with. And if we go back to yesterday, we're going to see that this one follows. I know, I get so good at these over time. I look forward to seeing everybody's homework because typically, like, they look like a disaster sometimes, which is okay. That's the point of learning, right? Is that we are getting better and better. So I have no problems if your drawings are kind of messy, so long as I can understand them. So, but yeah. Anyways, so remember that AX2E2 is bent always, molecularly speaking, and so this tells us also that it is polar. Remembering that all bent molecules will be polar, but if we wanted, we could draw a line through this. So there are a couple of lines we could draw. Okay, Maya, well, what you might want to do is, instead of watching this one right now, go watch the other one and then watch this one later. Maybe that might help, but we'll see. So if we draw one this way, we're going to say, oh wait, but look, it's the same. But if we draw our line over here, you see it's definitely not the same. Remember, for a molecule to be symmetrical, you have to be able to draw the line kind of anywhere. And if anywhere you draw it, it is not changing, then it's going to be symmetrical. So here we definitely do not have symmetry, right? If we cut the sulfur that way, we have 2 lone pairs on the top, 2 chlorines on the bottom. Definitely not the same thing. So, but again, easy way for us to know that the shape of it will tell us whether it's polar or not. If we go back to this guy, trust me, try it any way you like. whatever, any way you like to cut this molecule up, you'll see it's going to be the same on both sides. So that one is for sure symmetrical. Whereas this one, you're going to see that if you cut it in different ways, it'll not be symmetrical. It's like a spider web. Okay. And the other one we had was selenium dioxide. We for sure did that one yesterday. Sulfur, no, selenium. All right, so remember that structure from yesterday. Looking at it, it has a lone pair on it. Lone pair will always tell us, guess what? It's polar. And if we want to remember, it's the AX2E. That's polar. It's also bent, right? Just like the sulfur dichloride was. And again, if we were to draw a line, look, here we go. Lone pair on the top, 2 oxygens on the bottom. Different. Just so you know, we're only looking at kind of the domains here. We don't care about double bonds. So it does not matter for us if one of these oxygens is single bonded, the other is double bonded. Does not matter to us. Let's see, let's do maybe 2 more. We can look at a couple more molecules that we've had before. We had formaldehyde, right? And let's see, what other ones can I give you? How about two trigonal planar molecules here. Oh, shame on me, I've forgotten my lone pairs. These are all molecules we've done before, so if you do not remember these structures, just go back to the notes from either yesterday or Monday, and you'll see how to draw them. So, looking at these ones, let's see if we can identify which ones are polar or nonpolar, or if they are polar or nonpolar. What do we think about formaldehyde? Both of these, by the way, are AX3. AX3 does not tell us right away if it's polar or not. So we cannot immediately say polar, nonpolar. So what do we think, Sherry or Lamonda? Or whoever the mystery fourth person is. Or I don't know if Maya's still here. Yeah, I agree. This one, take a look. We cut it. Oxygen on one side, fluoride on the other side. Not so great. Yeah. So this one will be polar. Did I erase something? Oh, yes, I erased my sad face. And lo and behold, if we do it another way, same thing, same thing, same thing. All these guys will be, this one will be nonpolar. Another way to look at this is everything on our central atom is the same. So because everything's the same, just like carbon dioxide, they're going to be pulling equally. So this poor boron in there is being pulled in 3 different directions now, but they're all pulling equally strong, and so we're not going to have any polarity. So to kind of summarize this thing, here are some easy ways to kind of look at this. It's symmetrical. Everything is, or all electron domains will make it fancy, are identical. Whereas with a polar one, we saw that this was not symmetrical. Or it could have anything with a lone pair. Any that are bent or trigonal pyramid will be polar. One thing that I kind of glossed over is that all hydrocarbons will be nonpolar as well. So we saw methane, right? Completely symmetrical. If we take another molecule, maybe a little bit more complicated, here is ethane. It's also going to be completely the same. Yeah, you will never see a double bond on F, but it would still be nonpolar. So if some crazy... okay. Carbonate. If we pretend this is not an ion, even though it's an ion, these oxygens would all pull pretty much equally. So we would not worry about one of them pulling more. So we would technically say this is nonpolar. However, it is an ion, so that means it has charge already. So, but ignoring that, if we pretend that this didn't have a charge, okay, you know what? I'll do one more for you. I will give you a real molecule. Oh, but this has all double bond. Oh, fine, forget it. Never mind. It doesn't matter. For Lamonda, we would still say nonpolar. Cool. I'm going to erase this because I don't want to bring ions into this mess. And go ahead, look at all these hydrocarbons we've got here. Double bonds are stronger, yes. We're going to see that those are harder to break because essentially you're breaking 2 bonds instead of 1. So look at all these lovely hydrocarbons. We're going to see, look, they're totally symmetrical. Hooray. So all of our hydrocarbons, that is going to be something that is made of carbon and hydrogen in whatever amounts, will be nonpolar as well. So these are for molecules. Remember, polar bonds can be in both of these, right? Carbon dioxide was definitely a polar bond. It had polar bonds, but because it's symmetrical overall, the molecule is nonpolar. These are all hydrocarbons. All nonpolar. Okay. What's the point? So here we have a jar of water. I guess I should draw it as a straight line. Woo. And I'm going to put some oil in it. Ooh, can we see that yellow? I guess we can. It's horrible. Here, I'll make it orange. It's a little bit easier on our eyes. I don't like the yellow. Oh, you can see it? Well, anyways, I think orange is the easier to see anyway, so. We have all seen this in our lives. Just so you know, oil is essentially a hydrocarbon. Or you could say gasoline, those are hydrocarbons as well. They will also separate from water. And anyways, so we're going to see here that, remember, because it's a hydrocarbon, that means it's nonpolar. Water, of course, we have already seen was polar. And so that tells us, or using our, basic cooking skills or observation skills, these do not mix. Nonpolar stuff will want to be with nonpolar stuff. Polar stuff wants to be with polar stuff. So we have this idea of like dissolves like. And so that means polar we're going to see that this means that polar stuff wants to hang out with polar stuff, nonpolar stuff likes to hang out with nonpolar stuff. So let's put some iodine into the mixture. Where will the iodine go? Yes, it is. So that technically we're going to talk about in 2 chapters, but yeah, that's the idea. So stuff that is, we can say hydrophilic and hydrophobic are more specific cases, but it's the same idea. I'm not even going to write that right now. But yeah, that's the idea, for sure. So iodine's Lewis structure. What do we think? Is this going to be polar or not? We kind of have just a bond here. Let's look at that. Iodine's electronegativity, according to my handy chart, is 2.66. 2.66 minus 2.66 is 0. So we have a nonpolar bond. And is this thing symmetrical? We don't really have a central atom, but let's try and draw something down the middle. Looks to be the same on both sides. Of course, this thing is going to be nonpolar. So what's going to happen now is, if we now, you know what? Let's see if I can be fancy here. Okay, I can do this. Copy. How exciting. Okay, how the heck do I paste it? Oh, like that. Oh, how cool. Oh, how wonderful. I'm so excited. Nerdgasm here. Okay. Iodine, we throw it in. It's practice tomorrow, Maya. So I'm going to answer questions. If there's anything else you want me to re-go over, I'll do that. So iodine is a gray solid, and it turns purple in solution. So we're going to chunk in our iodine here. Iodine's pretty dense, so it'll sink to the bottom. And we're going to see that if we shake this stuff up, what's going to happen... Oh no, our beaker has exploded. The iodine will... Oh, goodness gracious. If we shake this guy up, that's our iodine, by the way. If we shake it up, it's going to end up turning that purple. The oil is going to turn purple. I'm not sure. I think I had a video of this in the textbook. But that's the idea here. It's very easy for us to see where the iodine went because it's going to turn wherever it went purple. So since we did not have anything purple at the start, once we shake it up, allow it to dissolve, it's going to turn the oil part purple. And that tells us that the I2 dissolved in the oil. And we know that I2 is nonpolar, and the oil is nonpolar as well. And so that's why those two are going to mix together. And since water is polar, it is not going to dissolve our iodine. And so not going to work there. Medically, you probably have heard of iodine as something to help sterilize or sanitize, rather. You know, skin or whatever. Betadine is an iodine-based disinfectant. You're going to see that iodine is typically dissolved in ethanol. Or it's got something else in it, like potassium iodide, to just help convince the iodine to dissolve in the water. So typically it's ethanol-based, just because the iodine will dissolve better in ethanol, because ethanol is a little bit more nonpolar. Ethanol has both kind of polar and nonpolar characteristics, so it could go either way. And we're going to see that that's going to help to dissolve the iodine. And so sometimes you'll have multiple solvents together. It gets crazy. But anyways, so there's a method to the madness here. So if you're ever asked to dissolve something and see where it's going to go, you have to kind of either draw the Lewis structure or already know the polarity of whatever it is you're dissolving. And so that's going to determine where things are going to dissolve, or if they're going to mix together. By the way, we have a fancy term. It's called miscible. It means two liquids will mix together. The opposite of that is immiscible, which means they don't mix. So that's going to be our oil and water will be immiscible, whereas water and ethanol, however, are miscible. They will mix together indefinitely, whereas immiscible ones will not mix. Okay, so there's our last little vocabulary for the day. And these specifically refer to liquids, so no solids here. Okay, so we are done with 5B now. So your exam next week is on chapter 4, which was electrons and like electron configurations and all. Wait, do we have an exam next week? Or is that just 111? Let me pull up the syllabus. 101. Yes. Let's find out. Yeah, it looks like you do have an exam on Monday. Cool, yeah. So that being the case, it is just on 4, 5A, and 5B. So that is on the electron stuff, as well as the naming and like ion charges, all that fun stuff. And then as well as these Lewis structures and the polarity. So all that worksheet stuff that you have this week will cover all of Chapter 5B. So it's going to cover Lewis structures, shapes, and polarity. Exciting. So, yep, I'm happy to answer questions tomorrow, but just like the exam review was last time, you guys have to bring questions, okay? So, yeah, so either have homework questions or just like, hey, can you go over another problem on predicting polarity or whatever, or electron configuration, and then we can do it. Okay? So with that, we'll see you tomorrow. Next week, since we have the exam, I'll probably do an exam review on Thursday if you guys want, so we can go over questions again for that. So, okay. With that, I will see you tomorrow if you want to. No new material tomorrow, so it's just gonna be going over stuff again. Okay. Take care.